So we're going to talk about Green's theorem. This is the second of the major integral theorems that we're going to talk about in this vector calculus chapter. The first one was the fundamental theorem for line integrals. So what Green's theorem is going to allow us to do is to integrate line integrals of vector fields around simple closed curve. So what is a simple closed curve? We already went over what a closed curve is. That's just a curve that has the same initial and terminal point, so it ends where it starts. And the simple part just means it doesn't intersect itself, so it can't cross over itself at some point. So over a simple closed curve, we're going to be integrating. Now, if you have a continuously differentiable vector field, and let's say that we know that this partial q with respect to x is equal to partial p with respect to y. That was one of the equivalent conditions for the vector field to be conservative. Okay? So Green's theorem is not really going to help us much for conservative vector fields. Because if we have a conservative vector field, we saw that one of the equivalent conditions for that, if you think about independence of path, is that around closed curves, you always get zero. So Green's theorem is really helping us for the non-conservative vector fields. And this is the idea of circulation. So the circulation of a vector field about a simple closed curve is defined to be this line integral. Okay, and this notation here, so this integral symbol with the little circle here, there's no new definition here. It's just indicating that we're integrating around a simple closed curve. If you don't include the circle, it's not wrong, but it's just included, just for a reminder to you when you're reading it. So, if f is conservative, then this integral of this p dx plus q dy, that has to be zero. Okay. So what if we had a non-conservative vector field? That's what we're really interested in. In that case, it's not really clear exactly what would be the best way to evaluate one of these. You have to set up a parameterization. It might be really messy. It might not be so nice. So what Green's theorem is going to do is give us a result that's going to relate the circulation around this simple closed curve to a double integral taken on the region inside, so the region bounded by the curve. And this is getting at all of these results that we're doing. Remember I said that they're going to be related in a certain way. So they're relating values of a function inside a region or inside something to values of something else on the boundary. Okay, I'm still kind of putting it in a vague way because we don't quite have the language to talk about it. But that's really what the fundamental theorem of calculus says. It says if you want to integrate a continuous function, then you can do that if you know the values of the antiderivative at the endpoints, the boundary. So what this is going to do is it's going to say if you know the values of a certain expression inside the simple closed curve, and we'll go over what that is, and you double integrate that, then that's the same as the line integral taken around the boundary, which is the curve. And this is going to be useful in both directions. Sometimes the line integral is hard to compute, and you can convert it to a double integral. Sometimes the double integral may be difficult to find, in which case you can just make it into a line integral. But it's really important for applications and also theoretically. So I'm going to go over the general statement of Green's theorem and then prove it in a very particular case over a simple region, which just means it's a region that's type 1 and type 2. Remember type 1 and type 2 from double integrals. So if you have both of those types, then that's the kind that we're going to be looking at. The general proof is a little bit beyond what we can do here, but you can prove it also in general. All right, so let's go to the statement here. So we're going to start off with some standard stuff that we've been doing for a while. So let C be a positively oriented, so that means counterclockwise, piecewise smooth, simple closed curve in the plane, and we're going to let D be the region bounded by C, so interior to C. Now, our vector field needs to be continuously differentiable on an open region containing D. So it has to be continuously differentiable, not just in the interior of the curve and on the curve, but just a little bit beyond it. And if you don't remember what continuously differentiable means, it means that all the first partial derivatives exist and are themselves continuous. And so a shorthand for continuously differentiable is a C1, so a C1 vector field. And we're also going to say F is equal to Pi plus Qj. So those are the components of F here. Then the conclusion is the following. So it says that the line integral around this simple closed curve C of P dx plus Q dy, so remember that's really the same as the integral of F dot dr, this is equal to the double integral over D of the partial of Q with respect to X minus the partial of P with respect to Y, dA. Okay, so it's relating the line integral along the boundary to a double integral of something else on the interior. Okay, so again, this is tricky to prove, but we're going to do it for a special case where it's a particular kind of region. So let's suppose that D is a simple region. So that means, and this, I'm not sure this is a standard term, but that means like a type 1 and type 2 region. Now the way we're going to go about this is we're going to show two things. So first, actually we're only going to do one here because the other one is extremely similar and it's a good exercise for you to do the second part of it after you've seen the first. So we're going to show that the integral of P dx is equal to minus the integral, double integral over D of partial of P with respect to Y dA. Okay, and then what's going to happen is the integral of Q dy then will be the double integral of partial Q with respect to X. And so when you add them together, you get that. But for now, let's just look at this piece. We're just going this to be equal to this. So since D is a type 1 region, that means it looks like this. So let's say this on top is G2 of X. And on the bottom, so this is Y equals G2 of X. And on the bottom, this is the graph of Y equals G1 of X. This is what it means to be a type 1 region. So between A and B. Now we can split this up then into 4 pieces. So let's say that this is C1, then we're going to go over C2, C3, and then back over here, C4. And this picture is kind of for dramatic purposes, and it doesn't necessarily have to look exactly like this, but we do know that there's 2 values, A and B, and it's everything between these 2 functions, graphs of these 2 functions between A and B. So the integral around C is just C1, C2, C3, C4. So one way you could write this is to say D is equal to, the set of all x, y, so that x is between A and B and y is between G1 of X and G2 of X. All right, so now 2 of these pieces are going to go away really quickly. So if you look at the 2 vertical pieces on C2 and C4, which, by the way, those could be just degenerate. In other words, they may just be a single point. But in general, we have to think about if we are actually going up like this. So along those 2, notice that since x is constant, dx is 0. So x is not changing. Same thing along C4. Dx is 0. So along C2 and C4, dx equals 0. So that means the integral along C2 of p dx is equal to the integral along C4. And these are both 0. So they just completely go away. So really we're only looking at C1 and C3. So let's look at C1 first. So the integral along C1, let me move this just a minute. There we go. So the integral along C1, we're looking at p of xy dx. Okay. But we know that along C1, a point along C1 is not just xy, so like a point right there. It doesn't have just coordinates xy, it has coordinates x, g1 of x, because it's on the lower boundary. So this is really the integral, and then since I'm integrating with respect to x, I don't have to parameterize this with t. I can just say, well, this is just, x going from a to b. And so this is now p of x, g1 of x, dx. Now, by a similar token, I could go along C3, and it's going to be pretty much the same with G2. The only difference is we're going the opposite direction, right? So instead of going from A to B, we're going from B to A. So that means I get the integral along C3 of p of xy dx is going to be minus the integral from A to B of p of x g2 of x dx. Now, when I put these together, this means, I'm going to add up C1, C2, C3, C4. So C2 and C4 were just 0. So really I'm just adding C1 and C3. So that gives me the integral around C of p dx is equal to, so it's going to be the integral from A to B of p of x, g1 of x, minus p of x, g2 of x, dx. So all this. Okay, so that's the left-hand side. That's the integral. Now what I have to do is say, well, what is the double integral? So this double integral of partial p with respect to y. And I should get the opposite, right? These are supposed to be opposites. So let's check out what that is. Since this is a type 1 region, I can set this up as an iterated integral. I'm going to go, x is going to go from a to b. And then for a fixed x, y goes from g1 of x up to g2 of x. And I'm integrating the partial of p with respect to y, which is itself a function of x and y, dy dx. Now let's think about evaluating this iterated integral. I start off by integrating with respect to y. Well, what is the integral with respect to y of the partial of p with respect to y? That's just going to be p of xy. Okay, plus some function of x, but it's just going to be p of xy. So that's going to give me the integral from a to b of p of xy evaluated between g1 of x and g2 of x. Now I'm substituting in here for y, and then I'm integrating dx. All right, so let's see what that gives me. That's going to give me the integral from a to b of p of x g2 of x minus p of x g1 of x. I'm just literally substituting in g1 of x and g2 of x in for y, just like that, and then subtracting. And I'm integrating all of this now dx. Now notice that is exactly the opposite of what I got up here. So let me highlight this. So that was the left-hand side. This is the right-hand side. Those are exactly the opposite of each other. So that shows that this up here, that shows that the integral around C is minus the double integral of this partial p with respect to y dA. So let me just note that. We have shown integral p dx is equal to minus double integral of this. And then I'm just going to say, and I'll leave this to you to go through the steps on your own. It's a good exercise. A similar argument. So you set it up as a type 2 region, and you follow much the same attack. So a similar argument shows that the integral of q dy is equal to, so it's not minus, it's positive, the double integral of q dx. Okay, and then these two together are Green's theorem. Okay, so that's the proof in this particular case. So let's look at a couple examples. We're going to verify it by doing both ways. We'll do the line integral and we'll do the double integral and see that we get the same answer. All right, we're going to look at a triangle. So positively oriented triangle, vertices at the origin, 1, 1, and 0, 1. Okay, so let's make a quick graph of this. So this is C. Now we need to split this up into some pieces. So let's start at the origin. Let's say that going this way is C1. Let's go this way, C2, and down this way, C3. And then everything inside here, this is D in here. Okay, so we're going to do, let's do the circulation first directly. So let's take a look at that. So we're going to be integrating x squared y dy minus y squared x dx. Okay, so let's first look along C1. Notice that on C1, this is the graph of y equals x, right? Because this is the point 1, 1. So along there, y is equal to x, which also means dy is equal to dx. So we can kind of do a little trick here. We can show then that the integral, so the integral along C1, so it's x squared y dy minus y squared x dx. But since x is equal to y, then this is really just the integral of x cubed. And since dy is dx, I can just change all the y's to x's. So I can make y into x, dy into dx. So it's going to be x cubed dx minus x cubed dx. And lo and behold, that's just integrating 0. So I end up getting 0 along there. So that's C1. Let's see, what about C2? Well, along C2, y is equal to 1, and dy is equal to 0, since y is constant. So that means the integral along C2 of x squared y dy minus y squared x dx is equal to, now we have to be careful here, so since dy is 0, that means all of this is going to go away. And since y is 1, that means y squared goes away. So really, we're just integrating minus x dx. Now, x goes from 1 to 0. So we're going in the negative direction. So I can set that up as an ordinary integral from 0 to 1 if I just change the sign. So it's the integral along C2 of minus x dx, which is the integral, here's the way I'll put it. So the minus sign in the minus x, I can change the direction here. So that's the same as the integral of x dx going in the opposite direction, but minus C2 is just going from 0, 1 to 1, 1. So that means x is just going from 0 to 1. So I'm just integrating from 0 to 1 x dx. which of course is x squared over 2, which is a half. Okay, so I get a half for that piece. All right, we got one more. We're just about done. C3. Well, along C3, let's see. X is equal to 0, and dx is equal to 0. So that means since each term here has a 0, so x is 0, that means the first term is going to be 0, dx is 0, the second term is going to be 0. Well, yeah, they're both going to be 0 because x is 0. So the integral along C3 is just going to be equal to 0. Okay, because the integrand is just 0. So altogether, the integral along C is equal to 0 plus a half plus 0 is equal to 1/2. All right, now we're going to use the double integral to evaluate this. Okay, so let's see how we would set this up. We're going to have x go from 0 to 1, and then y could go from x up to 1. We could also go y from 0 to 1. Actually, why don't we do it the other way? Let's go y from 0 to 1, and then x is going to go from 0 up to y. That's going to be maybe a little bit easier. So this is going to be the double integral. So we're going from y equals 0 up to 1, and then x is going to run from 0 up to y. Now, what's the partial of q with respect to x? So let's go up here. You have to be super careful on this one, because it's written in the opposite way. It's dy and then dx. So actually, p of xy is the minus y squared x, and q of xy is x squared y. So that means partial, let's just do it on the side here, partial q with respect to x minus partial p with respect to y. Q with respect to x is going to be 2xy minus partial p with respect to y is minus 2xy. All right, so that's going to be 4xy. So we're going to be integrating 4xy. So let's go down and do that. And this is dx dy. Okay, the 4 can come out. No big deal there. Now we're integrating xy with respect to x. That's going to be x squared y over 2. So x squared y over 2 from 0 to y. So we're substituting in for x. So that's going to be y, let's see, y cubed over 2 dy. Okay, so 4 and 2 cancel. And now I'm integrating y cubed, so it's going to be y to the 4th over 4 from 0 to 1. And lo and behold, I get 2/4, which is 1/2. So I have verified Green's theorem for this particular example. All right, so maybe you're not convinced by that. Let's look at another one. It's a slightly more complicated region. So we're going to verify Green's theorem for the vector field y squared x squared on the semi-annular region. So this just means it's the upper half of the annulus. So it's all the points whose in polar coordinates the radius is going to be between 1 and 3 and in the upper half plane. So all the xy, x squared plus y squared between 1 and 9, y bigger than or equal to 0. So we can draw a quick sketch of this. Okay, good enough for government purposes. So now let's look at the orientation. So it's got to be positively oriented. So it's going to go this way, around, there, 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 there. Okay, so you see all the way around. Now, how many pieces is this made up of? Well, there's going to be 4. So let's, it doesn't really matter how you order these. let's say that we start off with the inner kind of circular part here. So let's call this C1, and then this is going to be C2, all the way around C3, and then this little piece down here, C4. Okay, and it's this region that is D. So that's D. Okay, so let's do the line integral first. Y squared dx plus x squared dy. So let's look at C2 and C4 first. So notice that for C2 and C4, along there, y is equal to 0. Along each of those, y is equal to 0, and dy is equal to 0. And so that means that the integral along C2 is going to equal the integral along C4, which is just going to be 0. So we really only need to worry about C1 and C3. Now, these are very similar, if you notice. The only difference really between them is two things. First, they're different radius. One's radius 3 from the origin, the other one's radius 1. And they're going different directions. But we can do each of them at once, and then we can put everything together. So let's I'm going to call this C tilde sub A. So I'm going to let this be a positively oriented half circle centered at the origin with radius A. So it's going to be r of t is equal to a cosine t, a sine t, where t goes from 0 to pi. Okay, so just start over at, so for instance, if a is 3, we get exactly C3. If a is 1, we get the opposite of C1. Let's see, we're going to get the integral, let's do this over this general kind of path here. So this would be y squared dx plus x squared dy, which means we're going to integrate from 0 to pi of, so y squared is going to be a squared sine squared. Now dx, so remember this is x, this is x, this is y. Dx then is a sine t plus x squared, so a squared cosine squared, times dy, which is a cosine t. And whoops, I forgot a minus sign. So of course the derivative of cosine is minus sign, so there should be a minus sign right there. And all this dt. Now this is going to simplify because we can pull out an a cubed. So let's go ahead and do that. There's a squared a squared a, so that's going to be an a cubed out here. And so it looks like we got cosine cubed minus sine cubed. Now this might look horrible until you remember that for odd powers of sine and cosine, they're really not that bad, because we can just pull out one of them, one of the factors. So I'm going to do this kind of quickly. So I'm going to write this as cosine t times 1 minus sine squared. Okay, so that's cosine times cosine squared. That's cosine cubed. And then plus a minus sine. I need sine squared, which is also 1 minus cosine squared. And the reason I'm writing it like this is you can think of each of these as a little u substitution. Here I could let u equal sine, and there's my du sitting right there. Here I could let u equals cosine. So I'm kind of leaving it to you to kind of mentally think through these u substitutions in your head. But what you should end up coming up with is this is a cubed times, so here I'm going to get 1 minus u squared, so it's going to be u. So that's going to be sine minus sine cubed over 3. And then over here I'm going to get plus cosine and then minus cosine cubed over 3. And I have to evaluate this between 0 and pi. Now each of these first two terms goes away. And so this quickly evaluates to something pretty nice. So this is going to be a cubed times, now cosine of pi is -1 and cosine of 0 is 1. So this ends up making a cubed times, I'll let you check this on your own, it's -4/3. So we get a -4a cubed over 3. Now, we can use this to find, as I said, the integral along C1. Well, let's do C3 first. The integral along C3 is going to be the same as going around 3, which is going to be -4/3 3 cubed. And so it's going to be -4/3 27. The integral around C1 is going to be minus the integral around one of these with radius 1, which would be -4/3 times, of course, 1 cubed, so -4/3. Except it'd be positive because we're taking the opposite. So that means now if I add up all of these, I get the integral C1 plus C2 plus C3 plus C4, since these two made 0, and then what I have from these two is 4/3, and I've got a -27 plus 1, so that's 4 times -26 over 3. Finally, I get to -104 over 3. All right, now let's look at the double integral, and I think you'll find that this one's going to be a little bit easier. Now let's think about our region. Our region is going to be in polar coordinates, so we're going to go from, theta is going to go from 0 to pi, r is going to go from 1 to 3. What is this? Well, let's see. Partial q. What was q? Q was x squared. So the partial of q with respect to x is just 2x. And the partial of p with respect to y is just 2y. So it's just 2x minus y. And, whoops. So I need to change this into polar coordinates. So this is going to be 2 r cosine theta minus r sine theta. And I need a r dr d theta. And the nice thing about this is it splits up into an r integral and a theta integral. So it's 0 to pi of cosine theta minus sine theta d theta times, and then we've got r from 1 to 3 of, it's an r squared dr. Okay, so this is 2 times, this is sine minus cosine, 0 to pi, and this is r cubed over 3 from 1 to 3. So, this is going to go out at each of those, so we're going to get 2 times, this ends up being sorry, this should be positive here. This ends up being a -2, and then we've got 27 minus 1 over 3, so we get the same -4 26 over 3, so the same -104 over 3. Okay, so that's a couple of examples verifying Green's theorem. We're going to look at some more examples later, and then we'll see later that this is, again, just a particular case of Stokes' theorem, which is kind of a surface integral version of this.